Nuclear particles. This is just a list of them.
Okay, nuclear particles. There's lots of different nuclear particles. We're just going to go through and show you what they are and the isotope notation for each of them.
More or less, you just need to memorize the isotope notation for the podcast that follows this. These are the different particles we're going to be talking about for nuclear chemistry. All right, our first particle is going to be the alpha particle, which is really just a helium atom with no electrons.
Okay.
It has a mass of 4 and 2 protons.
Yep. So you see the isotope notation, you got the 4 on the top, 2 on the bottom, just like we did with all the other isotope notations. And normally when we see this particle, we're not going to write the +2 charge. It just should be understood after this point that the alpha particle is a helium nucleus, essentially, no electrons.
Not a helium atom, just the nucleus with no electrons. We're going to talk about this one a lot. The second one is a beta particle. Now, if we look at the isotope notation there, the top number is the mass.
It doesn't have mass, it's 0.
It has no mass.
It means no protons and no neutrons.
But it does have a -1 down there where the protons normally are. Are there any particles you can think of that have no mass and a negative charge?
Electrons.
A beta particle is really just an electron. It can be written either way with the Greek letter beta or the symbol E for electron, but no mass, -1 charge, that's a beta particle.
Nice. That one's easy.
Also very common. The third most common type is the gamma ray.
So this isn't a particle, I noticed.
No, it's a ray. Rays have to do with energy. There's the gamma symbol, that is the Greek letter gamma. An interesting thing about energy has no mass and no charge. It's energy. It's
so 0, 0.
0, 0.
Yeah.
It's just energy is given off in the form of a gamma ray. So that actually is going to make some of the equations pretty simple. Those are the 3 most common types, and if you think about the size of them and what they're made up of, they can travel through different things based on their size.
So the alpha particle is the biggest of all of them, being a helium nucleus. It can travel through the least. It actually can be stopped by paper. So, however, alpha particles actually are the most damaging of particles since they're so big, but they can't get through very much since they are so big as well.
So you can see there's 2 protons and 2 neutrons in the alpha particle. Compare that to the beta particle, which is just a single electron. It can go through paper, it can go through your hand, but it's stopped by a block of wood or a piece of metal.
Okay, so beta's kind of in the middle, and then we got the gamma particle, or I should say gamma ray.
Gamma ray energy
has no mass, so gamma rays can get through a lot of things. It's really only stopped by concrete or lead.
This is why Superman can't see through Lex Luthor's lead box.
Oh,
because the gamma rays don't come through.
Nice.
The lead box blocks the gamma rays from the kryptonite.
Also, why you would put a lead vest on to some extent when you get X-rays at the dentist. They put some lead on your lap so that it doesn't mess up your kids for later in life.
That would be the more practical application because Superman's not real. Another one that we're going to talk about sometimes in nuclear chemistry is a proton. So there's the symbol P. That is a lowercase p for proton, not phosphorus. And let's just think about isotope notation for a second. Well, you've got a mass and an atomic number.
If it's a proton, then it obviously has at least 1 proton, right? By
True.
definition, a proton is 1 proton.
True. And there's no neutrons because, well, it's a proton. So it has a mass of 1 and a charge of 1, an atomic number of 1. Okay?
Nice.
Proton, mass of 1, charge of 1. A neutron is the other one. Let's apply that same logic to the neutron.
So it's a neutron, so it's not a proton, so neutron means no protons.
No protons, sort of. And neutrons have, what is their mass?
Well, a neutron's mass is 1.
It's also
just
1.
Like a proton.
And it doesn't have a charge. So 1, 0 means neutron. Mass of 1 with no charge, no protons. The last one is a positron.
This one sounds funky.
Is that even real? That's not a real word.
I think it is.
Positron.
It sounds positive.
It sounds something like out of Star Trek.
It's much more positive than negative.
Okay, a positron. Well, what's a positron?
That's a good
it
question.
Sounds like it's a positive electron. It's a positive electron.
Nice.
So you take the same thing you have with an electron, no mass, and a positive one charge, because it is a positive electron. It is actually the antiparticle to the electron. There is such a thing as antimatter, and you're looking at it. The positron is technically antimatter. And you can be written as the positive beta particle as well. So those are it. Those are the isotope notations you need to know for those atomic particles that we will use when talking about radioactive decay.